My dear learners, once again we've met to discuss the last unit of our general chemistry course, EBS132. I'm very optimistic that you are not relenting in your efforts in studying. I want to urge you to continue studying whilst you are home, because very soon we'll be coming back to campus for us to meet face to face to put finishing touches to our studies. Then you can write your examination. I also want to emphasize the fact that whilst you are home, you continue to observe all the protocols that have been put in place to prevent us from contracting COVID-19. It is very, very rare. And so talking about keeping a social distance of 1 meter, washing your hands frequently, putting on the face mask, as well as applying the alcohol-based hand sanitizer. Don't joke with them. Practice all of them whilst you are home so that you will be safe and sound before you come back to school. Again, most of the time as students, we have the misconception that concepts in chemistry are very difficult. And for that matter, when we are about studying them, we block our minds. And once that is done, you realize that no matter all the efforts that are made, once your mind is blocked, you not get anything. I want to say that concepts in chemistry are very, very easy. Today we're going to look at organic chemistry, chemistry of carbon compounds. And most of the time when students hear this, they are tempted to think that it is something that probably when they were introduced to back at the SS level, they couldn't get it properly, and for that matter, that's how it's gonna be. No, it wouldn't be like that. I want you to free yourself, stay tuned, focused, and then listen attentively. And I'm sure that at the end of it, you will actually enjoy the organic chemistry that we are going to do. As usual, it's very important to talk about our performance indicators at the start of every discussion. And so by the end of this discussion that we are going to have, I expect you to be able to, one, classify and then name different types of organic compounds. You should also be able to describe the structures of different organic compounds. There are different organic compounds. You'll be in a position to describe their structures. You should also be able to discuss the properties of organic compounds as well. And finally, you should be in a position to describe the preparation and uses of some organic compounds. We have some of these compounds that we can prepare in the science lab. We can also talk about their uses. It's expected that at the end of this discussion, you will be in a position to actually describe the preparation for some of these organic compounds. In chemistry, we have two major compounds: organic compounds and inorganic compounds. When we talk of organic compounds, then we are talking about compounds which contain the element carbon. So the underlying word in organic compounds is the element carbon. Now, all compounds that have carbon in them, most of them are organic compounds, with the exception of very few of them that, even though they have carbon in them, they are not classified as organic compounds, but rather they are classified as inorganic compounds. A typical example of such compounds are carbon monoxide. The formula is CO. This is the soot that comes out through the exhaust of a car vehicle. Even though this compound contains carbon, it is not classified as an organic compound, but rather inorganic compound. Another example is carbon dioxide, CO2. This compound too, we all know it's with us. It has the element carbon in it, yet it is considered as an inorganic compound. Now, carbonate compounds such as calcium carbonate and carbonic acid are also classified as inorganic compounds. So when I talk of carbonates, I'm talking about CaCO3, that is calcium carbonate, and then I'm looking at H2CO3, that is a carbonic acid. All these compounds have carbon in them, yet they are not classified as organic compounds. So yet these are the very few compounds that have carbon in them, yet they are not classified as organic compounds, but rather inorganic compounds. So inorganic compounds are compounds generally that do not contain the element carbon. Examples, we can talk about sodium chloride, NaCl. We can talk about sodium hydroxide, NaOH. We can talk about hydrochloric acid or hydrogen chloride, HCl, and then many more. At this point, now we have talked about inorganic compounds and organic compounds. We are going to try the differences in detail between the two. However, I want to pause for a while for you to also think about some few inorganic compounds that you can talk about. We are saying that they are compounds that generally do not contain the element carbon. So you can think about a number of them and then add up to what we have given you. Now in details, if you are looking at the differences between organic and then inorganic compounds, then we can say that organic compounds are mostly covalent compounds. We have already studied covalent bonding and covalent compounds, ionic bonding, ionic compounds. So for now, if you mention covalent compounds, you should quickly be in a position to know that these are compounds that are formed as a result of sharing of electrons. On the other hand, inorganic compounds are mostly ionic compounds. And if they are ionic compounds, their formation is as a result of transfer of electrons from the electropositive to the electronegative compound, the electronegative elements as well. Now, organic compounds, they react at a slow rate. It means that their reaction is not fast or faster, it's very slow. Now, when you compare it to inorganic compounds, they react at a very fast rate. Organic compounds are highly volatile. When we say compounds are volatile, it means that they easily change into vapor form. A typical example is petrol. If you have petrol and then you open it up and you leave it for some time and then come back to it, you realize that the level with which you left it will not be the same as you come back to look at it. It means that they have changed from the liquid state into the vapor state. On the other hand, when you come to inorganic compounds, they are less volatile. It means that they don't change into vapor form rapidly. Now, most organic compounds are also soluble in organic solvent. For example, if you take kerosene, for instance, it's an organic compound. If you pour kerosene in water, you realize that it wouldn't form miscible solution. Rather, the kerosene will suspend on top of the water. What it means is that it is not soluble in it. Now, most inorganic compounds are mostly insoluble in organic solvent. They are rather soluble in non-organic solvent. So you put them in water and then they will dissolve. So for example, inorganic compound like sodium chloride, common salt. If you put common salt in water, it will dissolve. When you put it in organic solvent like kerosene, it will not dissolve. Now, organic compounds are highly inflammable. The word flammable and inflammable are used interchangeably to mean the same thing. It means that it easily catches fire. So where we have organic compounds, it's not advisable to be getting closer to the place with naked flame. If you joke with that, it can easily catch fire. Now, inorganic compounds are not flammable as compared to organic compounds. Again, organic compounds have low melting and boiling point. Inorganic compounds, they have high melting and boiling point. So if they have low melting point, boiling point, what it means is that if you are melting them, if you are boiling them, it requires a higher percentage of heat or temperature to be able to cause it to melt or to boil. If it is inorganic compounds, they have high melting point and boiling point. They rather require a high temperature and to be able to melt them and to boil them. But the organic compounds rather have low melting and boiling points. It means that they don't require a higher temperature to be able to melt them or boil them. We continue with our discussion with the organic chemistry in detail. So we said that it is the branch of chemistry which deals with carbon and carbon compounds that contain carbon-carbon bonds or carbon-carbon-hydrogen bonds, or both of them. Now, because we have said earlier on that organic chemistry, the underlying element is carbon, there is a particular characteristic of carbon which is very important that you need to know and be able to apply it to all the subsequent organic that you are going to study. And that is the fact that when you pick carbon, it can form a maximum of 4 bonds. Carbon form a maximum of 4 bonds. Now these 4 bonds, it does so by utilizing the 4 electrons that are found on the outermost shell of the carbon. You know, carbon is the 6th element, so the atomic number for carbon is 6. It means that there are 6 electrons that are found in carbon. Now, if you are drawing the electronic configuration for carbon, you realize that the very first shell will take 2 electrons. Now, if you have 6 and you put 2 on the first one, the outermost one, which is the valence shell, will have a maximum of 4 electrons. And it is these 4 electrons that carbon uses in the formation of the bond. So you realize that if you are talking about single bond, it can form 4 bonds. If it is an alkene that is a double bond, you realize that the double bond will indicate that the carbon-carbon have already formed 2 bonds. And for that matter, you can add only 2 bonds to the carbon, each of the carbon, to make up 4. So it's important that you take note. Most often when you are looking at the scripts of students, you realize that they are talking about alkynes, triple bonds, yet they have hydrocarbons, alkyne, about 3 hydrogens attached to a carbon, which makes it totally wrong. And that's an indication that the student like the concepts of the fact that carbon can form a maximum of 4 bonds, and for that matter, if there are 3 bonds there already, it's only 1 bond that can be added to it to make it form. Now, organic compounds have been classified. Now, the classification is based on structure and at the same time functional group. So we have 2 major ways by which we can classify organic compounds. We can classify organic compounds based on the structure of the molecule. Then we can also classify organic compounds based on the functional group that is present in the molecule. So here we have a flow chart of the classification of organic compounds based on structure. Take some time off, look at the structure very well, and then see the various classifications that can be given to organic compound on the basis of their structures. So on that, we have some that are classified as aliphatic compounds. Some are classified as heterocyclic compounds. Some are also put under alicyclic compounds. Then finally, we have aromatic compounds. Now briefly, when we talk of aliphatic compounds, what are we referring to? We are saying that these are the organic compounds that are straight in nature. Apart from the fact that they are straight chained, we can also have a branch chain attached to the straight chain. Now these compounds can be single, it can be multiple bonds. When I say multiple, I mean it can be double and then it can be triple. So all these fall under aliphatic compounds. When you take heterocyclic compounds, they are organic compounds containing close chain ring of carbon and other atoms. Other atoms here is very, very important because we realize that the heterocyclic and the alicyclic are very close. The difference in there is that with the heterocyclic, there are other compounds apart from the carbon, and with the alicyclic, it is only the rings of carbon atoms. So heterocyclic compounds contain close rings of carbon and other atoms, but alicyclic compounds contain close rings of carbon atoms alone. Now the next classification of organic compounds on the basis of structure is aromatic compounds. Now these aromatic compounds are compounds containing 1 or more benzene rings. Compounds containing 1 or more benzene rings. So if you want to talk in detail about the aliphatic compounds, we are saying they are the open chain organic compounds. They can be straight, they can be branched, they can be single or multiple bonds. So if you look at the example that is on the screen, you realize that we have a typical example of the aliphatic compound. The carbons are opened up. So if you come from left, we have 1, 2, 3, 4, 5, 6, 7, 8 octane. Now if you pick it from the right side, you have 1, 2, 3. The third carbon is having an ether, that is a branch from the main one. So this is a typical example of an aliphatic compound. If you look at alicyclic compounds, they are the organic compounds containing close rings of carbon atoms alone. Alicyclic, close rings of carbon atoms alone. And they are with localized bonding electrons as well. So a typical example is a cyclobutane. You see the structure of a cyclobutane on the board, and then we also have a cyclohexane. You realize that the rings of carbon are closed. The rings of carbon are closed. These ones have only carbon atoms. These are examples of hydrocarbons that are alicyclic in nature. And so because they are hydrocarbons, the core elements we see there are carbon and then hydrogen only. Now on the left side of the screen, you see that we have a model of this cyclobutane and then cyclohexane. Very soon when you come back to campus, some of these models are available in the science lab, and then we'll show you how to use some of these models to form some of this cyclobutane and then cyclohexane and others. The next one is heterocyclic organic compounds. These are compounds containing close rings of carbon and other atoms. Carbon and other atoms. With the alicyclic, we said that they contain close rings of carbon atoms alone. But with the heterocyclic organic compounds, they are compounds containing close rings of carbon and other atoms. So if you look at the examples that we have the furan and then we have the thiophene. With the furan, you see that the carbon and hydrogens are there. They are forming the close rings, but there is an additional atom that is the oxygen. And it is the presence of the oxygen that makes it a heterocyclic organic compound. Again, with the thiophene, you realize that it has the atom sulfur also attached to it. So the presence of the sulfur to the carbon makes it a heterocyclic organic compound. Again, you see the model of the furan as well as the thiophene on the left side. And like I've said, we will practice these models in the formation of these compounds when you come back to campus. Then we have aromatic compounds. These are compounds containing one or more benzene rings. So the rings that you see there, these are the ones that fall under aromatic, and we refer to them as benzene rings. Now, a typical example, we have naphthalene. In fact, naphthalene ball. You can also talk about camphor. All these are examples of aromatic compounds, and they have the benzene ring with them. Again, beneath each of them, the naphthalene and the benzene itself, you see the model of the structures of these compounds that we are talking about. Now we move on to hydrocarbons. What are hydrocarbons? And like the name suggests, hydrocarbons. These are organic compounds containing only hydrogen and carbon atoms. Only hydrogen and carbon atoms. So when you are asked what are hydrocarbons, they are organic compounds whose constituent elements are only carbon and hydrogen atoms. Now with that, we have aliphatic compounds that are hydrocarbons. So we have aliphatic hydrocarbons. A typical example is petroleum products, like for instance kerosene and petrol. These fall under aliphatic hydrocarbons. We can also have alicyclic hydrocarbons. So realize that all the classes of organic compounds that we had, the aliphatic, the alicyclic, the aromatic, the heterocyclic, all of them, we can have hydrocarbons falling under all of them. So with alicyclic hydrocarbons, we have an example of a cyclohexane. Then aromatic hydrocarbons, we can talk about benzene, we can talk about naphthalene. Now when we talk of aliphatic hydrocarbons, they are also grouped into three. The very first one is what we call alkane. So alkanes are the aliphatic compounds with carbon-carbon single bonds. So if you look on the screen, you realize that you see the structure of two carbons and the bonds are on it. Each of the carbon is having 3 bonds, and sandwiched between the two carbons is also another bond. And anytime a bond is formed, there are 2 electrons that make up that bond. So all alkanes are aliphatic compounds, and they have single bonds. Because they have single bonds, we can also classify them as saturated hydrocarbons. Saturated hydrocarbons. We can say that alkanes are saturated hydrocarbons because they have single carbon-carbon bonds. Now the next aliphatic hydrocarbon is alkene. Then we have alkyne. Take note that these hydrocarbons, we have what we call the stem, then the ending. In other words, we have the prefix and then the suffix. Now the stem is the prefix, that is what begins it, and that is for alkanes arc. Alkenes arc and the alkynes arc. Now when it comes to the ending, if it is alkane, you realize that it ends with ANE. Alkene is ENE and alkyne is YNE. Now all alkenes ending ENE are aliphatic compounds containing carbon-carbon double bonds. So you look at the functional group that is on the screen, and you see that between the 2 carbon atoms, we have double bond that is sandwiching between the 2 carbon atoms. Alkynes are aliphatic compounds containing 1 carbon-carbon triple bond. So again, you see the functional group of an alkyne, and it has a triple bond in between the carbon. Now, from the beginning, I said that carbon has a peculiar characteristics. That is the fact that it exhibits, it can form only 4 bonds. So if you go back to the alkane, the structure that you see there, you realize that the carbons of the bond that you see are single in nature. And because they are single, you can count 1, 2, 3, 4 bonds on. The bonds are what you see as a dash on the carbon. You can count 4 for each of the carbons. Now when you come to alkene, because carbon form a maximum of 4 bonds, in between the 2 carbon atoms, we have a double bond. So the double bond presupposes that it has already, each of the carbon bond has already formed 2 bonds. And so you can only put 2 additional bonds on each of the carbon to make up 4. The moment you make it 3 on each of the carbon like that of the alkane, then you are telling us that carbon can form 5 bonds, which is not correct. Because the 4 bonds that carbon forms, it uses the 4 electrons on its outermost or valence shell. And so if 2 electrons have already been used, it's only left with 2 electrons that can be used. So 2 bonds can be put on each of the carbon. Now when it comes to the alkyne, you see that it is characterized with triple bonds in between the 2 carbon atoms. So it means that each of the carbon is forming 3 bonds in between the carbon atoms. So if it has 3 bonds already, then you can only add 1 bond to it to make it 4. And that is why you see the structure like that. So take note of that. Now we want to look at saturated and unsaturated compounds. I have mentioned saturated when I was talking about alkanes. So saturated compounds are those containing only single covalent bond. And the typical examples are the compounds of alkane. So saturated hydrocarbon is an organic compound which contains carbon-carbon second bond with carbon and hydrogen atoms only. So take note that once it's a carbon-carbon single bond, then it is classified as saturated. A typical example is an alkane compound. Now alkanes are saturated hydrocarbons with only single bonds and have the general molecular formula CnH2n plus 2, where n is the number of carbon atoms, and in alkanes n start from 1. So it is this general molecular formula that is used in determining all the classes of alkane compounds. The very first one you can have is a methane. And how is that obtained? Methane has the formula CH4. Let's look at how you can use this general molecular formula to determine a methane. Now when N, which stands for the number of carbon atoms, is 1, then in place of N in this general molecular formula, you put the 1 there. So if I take off N and I put 1, I'm going to have C1 H2 times 1 plus 2. Now C1 means that you are multiplying C by 1, and that will give you a C. Now the hydrogen 2 times 1 will give you 2, plus 2 will give you 4. So when N is 1, you will have a CH4, which is methane. When N is 2, you put 2 in place of N in the equation or the general molecular formula, and then that will give you C2 H2 times 2, which is 4 plus 2, 6. And so the second alkane that can be obtained is a C2H6, and that is ethane. Now at this point I want you to look at when N is 3, when N is 4, when N is 5, the formula that can be obtained from this. When N is 6, you realize that in place of N in the general molecular formula, you put 6 there. So that will give you C6, H2 times 6 is 12, plus 2, 14. So you have 6 carbon atoms, and then you have 14 hydrogen atoms, and that will give you a hexane. So we are going to use this formula to study in detail the saturated hydrocarbons. Now when it comes to unsaturated compounds, they are those containing double and triple bonds. Earlier we mentioned that alkenes have double bond, alkynes have triple bonds. So the double bonds and the triple bond together constitute the multiple bonds, and these form the unsaturated compounds or the unsaturated hydrocarbons. So unsaturated hydrocarbon is an organic compound which contains multiple bonds with carbon and hydrogen atoms only. Again, when you say multiple, then you are talking about double bond and triple bond. So double bond specifically for alkene, and then triple bond for alkyne compounds. Now alkenes have the general formula CnH2n. So when N is 1 for an alkene, you have, now it's alkenes and then alkynes. It is the alkanes that N start from 1, but alkenes and alkynes N start from 2. So when N is 2, you have C2, H2 times 2 is 4, and that will give you C2H4. When it comes to alkyne, N also starts from 2. So when we put 2 in place of N, then we have C2 H2 times 2, which is 4 minus 2, which is 2. So that will give you C2H2, and that is an alkyne. These form unsaturated hydrocarbons. So as we continue, we will discuss this in detail, and then you get to know much about that. We mentioned functional groups along the discussion. When we talk of functional groups, what are we referring to? A functional group is an atom or a group of bonded atoms which gives an organic molecule its characteristic chemical properties. Now the molecules have physical properties and chemical properties. The chemical properties of these organic compounds are determined by their functional groups. So when you look at alkane, the suffix that is the ending, like I told you earlier on, is ANE. Its functional group is what you see there. 2 carbon atoms having a single bond in between the 2 atoms and 3 bonds on each of the carbon. When you look at alkene, it ends ENE, that is the suffix, and that is characterized with a double bond. So we have a double bond sandwiching between the 2 carbon atoms, and each of the carbon atoms also having 2 bonds together to form the functional group of alkene. Alkynes end with YNE, and then it also has 3 bonds in between the carbon atoms. So once there are 3, each of the carbon atom can only possess just a bond to add up to the 3 to make up 4. Alkanols end with OL, and the functional group of an alkanol is a bond to an OH. Then we have alkanoic acids, carboxylic acids as well. It ends with OIC, oic, and the functional group is a bond to a carbon with 2 oxygen atoms and a hydrogen. The structure of the alkanoic acid functional group is a bond to carbon, a double bond picking up 1 oxygen, and then a single bond also picking up oxygen and the hydrogen. The last one that we'll be considering is the alkyl-alkanoids, which are also called the esters. They end with OATE, and the functional group is R, an alkyl to a carbon, 2 oxygens to an alkyl prime, or the structure, we have a bond to the carbon, having double bond picking up 1 of the oxygen on top of it or on the diagonal of it, and then we have another bond from the carbon picking up an oxygen and another bond. So these are the functional group and their structures of the various classes of compounds. Take note that we have said a functional group is an atom or group of bonded atoms which gives an organic compound its characteristics, chemical properties. So the chemical properties of alkanes are determined by that functional group. Alkenes are also determined by the functional group of alkenes, and so on and so forth. Now I want to look at nomenclature of organic compounds. When we talk of nomenclature, we are talking about naming of organic compounds. Now, Inorganic system of naming organic compounds follows a system that form the namings. So namings of alkanes, if you want to look at that, of course alkanes are the fundamental compounds. So aliphatic organic compounds are either in the form of continuous chain, like what you see on the board. The example 1, 2, 3, 4, 5 carbons tells you that that structure you see there is pentane. So the name can be in a straight form like this. Then we can also have continuous chain with branch chain of carbon atoms or other elements attached to the continuous chain. So again, we can have the main chain, continuous carbon chain, and along the line we can have a branch chain like that. And anytime there is a branch, it forms what is called a substituent or a side group. So if you look at the second example that you see on the screen, you realize that we have the 1, 2, 3, 4, 5 carbons. So the parent name will give you a pentane. But now because we have a branch or a substituent, you look at the substituent, and as we move on, we'll talk about the rules that are used in the naming of this Inorganic system of compounds. So that is the branch chain. Now in naming continuous chain compounds, the Inorganic name consists of a root, that is a prefix, or a stem which indicates the number of carbon atoms in the continuous chain. A suffix which indicates the type of functional group present in the molecule is also considered. So now let's talk about the rules. Now if you want to name alkanes, first, when you are giving the compound, you count the longest continuous carbon chain and then you name it as the parent structure. You count the longest continuous carbon chain and then you name it as the parent structure. Then you add the suffix ane to the ending. Add the suffix ane to the ending. Now let's look at structures of some members of alkane family. So if you are using the CnH2n plus 2, which is the general molecular formula for alkanes, when n is 1, the first compound of an alkane you can obtain is the methane, and that is the structure of methane you see on the screen. A carbon having 4 bonds to hydrogen on each side of it. Now we see the structure using the model beneath it. The next one is ethane. That is when n is 2. So when n is 2, you put 2 in place of n, it will give you C2H2 times 2, which is 4 plus 2, 6. So you have 2 carbon atoms and then you have 6 hydrogen atoms forming ethane. and that is the structure you see beneath it. Now if N is 3, then you have propane. So that will be C3 H2 times 3, which is 6 plus 2, 8. So you have C3 H8, 3 carbon atoms and 8 hydrogen atoms forming propane. Then you have butane. Now with butane, we have 4 carbon atoms. So that is when N is 4. So in place of N, in the same CnH2n plus 2, you put 4 there, and that'll give you C4, and 2 times 4 is 8 plus 2, giving you 10. And the hydrogens will be 10. So if you count the hydrogen atoms on the butane, the 4 carbons, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's about butane. Now if it is pentane, how would it look like? Just take a short time and then think about it, taking into consideration the ones that we have discussed. Alright, you will see that for pentane, the carbon atoms will be 5. And if the carbon atoms are 5, in place of N in the equation, you put 5 there. And once you put 5 there, you have C5, and H 2 times 5 is 10 plus 2, making 12. So you have 5 carbon atoms and you have 12 hydrogen atoms on pentane. Now we continue with the nomenclature of organic compounds. Like I said, anytime you are given the compound, first count the longest continuous carbon chain in it. In counting, if you have just only one carbon, its root or prefix will be meth, M-E-T-H. If you have 2 carbons in the compound, it will give you a root or a prefix eth. If you have 3 carbons, it is a prop. 4 carbons will give you a boot. 5 carbons will give you a pent. 6 carbons will give you hex. 7 will give you hept. 8 will give you oct. 9 will give you non. 10 will give you dec. And 11 on decane. And then 12 will give you dodecane, and so on and so forth. So the Aliphatic name, when you have 1 carbon atom, will be a methane. When the carbon atoms are 2, it is ethane. When the carbon atoms are 3, you have propane. When you have 4 carbon atoms in the compound, it will give you a butane. When the carbon atoms are 5, pentane. 6 will give you hexane. 7 heptane. 8 octane. 9 onane. 10 decane. But at your level, I believe that you'll not be giving more than 8 carbon atoms. However, it's very important that you know all the others that we are considering. So we are continuing in the nomenclature, still talking about the rules. So in naming of alkanes with branch chain, that is the substituent. The parent name is given the longest continuous carbon chain. Then the branch chain becomes the substituent. Of course, we have 2 types of substituents. We have organic substituents, which are the alkyl groups, and an alkyl has a general formula CnH2n plus 1. Or in other words, an alkyl is an alkane that you have taken a hydrogen from it. So when you have an alkane like, for instance, methane, and then you subtract 1 hydrogen from it, it gives you an alkyl that is a methyl, and that is an organic substituent. We also have ether, which is also an organic substituent. Then we can have propyl and so on. On the other hand, when it comes to the inorganic substituent, we can talk about bromo, that is Br. We can talk about chloro, that is Cl. So you can have a compound that has a Cl attached to it as a substituent, or it has a Br attached to it as a substituent. We can also have an F, which is a fluoro. Then we can talk about a nitro and then amino as well. The names and position or positions of the substituents always precede the parent name. What it means is that if you are given an organic compound and you are naming, there is a substituent. It's the name of the substituent that will come first, followed by the parent name. So a substituent that contains 1 less hydrogen than the corresponding alkane is what is known as the alkyl group. It contains 1 less hydrogen than the corresponding alkane, and that is what is called an alkyl group. So when I have a methane and then I take one hydrogen from it, it gives me a methyl, which is an alkyl group. If I have ethane and I take one hydrogen from it, it will give me C2H5, and that is an ether, which is also an alkyl group. So an alkyl group is a group of hydrocarbon radical, that is group of atoms derived from an alkane by the removal of one hydrogen atom. Take note, by the removal of one hydrogen atom. Like I said, their general molecular formula is CnH2n plus 1, where n starts from 1. So if n is 1, then in place of n in the equation or in the general molecular formula, you put the 1 there, and that will give you C1, H2 times 1, 2 plus 1, 3. So you have CH3 as the meter. If you put 2 there, it's going to give you C2, H2 times 2, 4 plus 1, 5. So you have C2H5, and this is called ether. So the alkyl groups are named as you see on the screen. CH3 will give you a meter, and of course that is an alkane or a methane that one hydrogen has been taken away from it. CH2CH3 is an ether. In other words, it is C2H5, and that is also ethane that you have subtracted one hydrogen from it. A proper will give you CH2, CH2, CH3. That is C3H7, which is a proper. So all these are alkyl groups, and the structure of these are what you see on the screen. So meter, we have a carbon. Using the model, the carbon is at the center, and the 3 hydrogen atoms are what you see on it. With the ether, we have 2 carbon atoms, and then each of them is having, one is having 2 hydrogen atoms on it, and the other carbon atom is also having 3 hydrogen atoms, making 2 atoms of carbon and 5 atoms of hydrogen forming the ether. And these are alkyl groups, and they are organic substituents. Then we move on to the non-alkyl groups, which are the inorganic substituents. So for example, you can have Br on a compound, and the Br is called bromo. If you have Cl, it is chloro. If you have F, it is fluoro. If you have I, it is iodo. NH3 is amino, and NO2 is nitro. So these are inorganic substituents that you can have on any organic compound that is given to you to name. In naming, where we have organic substituent together with inorganic substituent, preference is given to the inorganic substituent. And so you number your carbon atoms in such a way that your inorganic substituent will be on the least carbon. Then the rules continue. Now the rules for naming aliphatic compounds, like we have started, we said always select the longest continuous carbon chain atoms in the molecule. So in counting the longest continuous carbon chain, if I have 1, it will give me a methane. If I have 2, it will give me a ethane. If I have 3, the stem will be a prop, and the ending will be ane, so it will give me propane, butane, and so on and so forth. So always select the longest continuous chain of carbon atom in the molecule. Now let's take a look at the example that we see on the screen. You realize that if you are picking up the longest chain, if you count the carbon chains horizontally, you have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now there is a branch on one of the carbon atoms. Now you don't from the beginning consider it as a branch. You still have to try it out and see if you can get the longest continuous chain from there. It's only when you don't get it that you consider it as a branch or as a substituent. So if you are taking it from the left side, the carbon atoms are 1, 2, 3, 4, 5 if you consider the branch. Then if you take it from the right side, you have 1, 2, 3, 4 if you consider the branch. But if you don't consider the branch that you see there, then the longest chain is 1, 2, 3, 4, 5, 6. That makes it a hexane. So the parent name for this compound that you see there is a hexane. Now after you have had the hexane, you put it aside. Then you look at the substituent that is there. If there is no substituent, you end there, that is its name. But once there is a substituent, you are now going to number the carbon atoms in such a way that the substituent will always be on the least carbon atom. So if you count the carbon atoms from the left side, you have 1, 2, 3, 4. You realize that that substituent meter is resting on the carbon number 4. When you pick it from the right side, if you count, you have 1, 2, 3, you realize that the meter is rather on carbon number 3. Now always it is the least that we want, and so strictly you have no option than to count or number your carbon atoms from the right side. So numbering from the right side, we have carbon number 1, carbon number 2, carbon number 3. It means that the meter CH3 is resting on carbon number 3, and this will make it a 3-meter hexane. 3-meter hexane. So in the example above, the longest chain has 6 carbon atoms. Hence the parent name is hexane, like I have said. Now you number the carbon atoms of the longest continuous chain and indicate the position of the substituent with the least number of carbon. The least number of carbon. That is what I said, that if you count from the left side, the meter will be on the carbon number 4. If you count from the right side, the meter will be on the carbon number 3. So because we always want the substituent to be on the least carbon, strictly we prefer counting from the right side to get the substituent on the carbon number 3, and that is what will give the correct name of that compound. If you don't do that and you take it from the left side, you will get the name wrong. So in the above example, the parent chain is hexane, the substituent is a meter, and the meter is on the 3rd carbon counting from the right, because that is where you will get the meter to be on the least carbon. And so like I said, that makes it a 3-meter hexane. So the position is position number 3 on the carbon atom, and therefore the name of the compound is 3-meter hexane. Take note that in naming, figures are separated from letters with a hyphen. Figures are separated from letters with a hyphen. Now numbers from numbers, or figures from figures, are separated by a comma. So as we continue with the discussion, we'll come across some of them that you realize that we will use a comma, we use a hyphen, and none of them are part of the naming. Now there are times you see a particular substituent appearing 2 or 3 or 4 times on the compound that you are giving. So if 2 or more of the same substituents are present on the parents, name them as di for 2, tri for 3, and tetra for 4, and indicate the position of each of these substituents that we are talking about. So when you see a particular substituent appearing 2, before you mention that name, for example, if you have bromo, one bromo, another bromo on the compound, before I'll mention bromo, I must introduce a di. And at the same time, I must indicate the position of the bromos on the carbons of the longest chain, and that will also form part of the naming. Now when the substituent appeared 3 times, it is indicated with a prefix tri. If there are 4, a tetra. Then in all the 3 and the 4 respectively, you indicate the position of the carbons on which these substituents are resting. So if you look at the example that you see on the screen, you realize that we have 2 of the substituent. The substituent now is in the condensed form. It can also be in the structured form like you saw in the earlier examples that I showed. This very one. We realize that the substituent CH3, we are using the structural or graphical structure. Now when you come to this example, you realize that the CH3s have been condensed. So an organic compound can be in the structural form, where you see all the bonds. It can be in the condensed form, and then you can also be in the molecular form. Now over here you see that there are 2 substituents. They are all meters, and the 2 meters are resting on the same carbon. So first of all, if you are given a compound like this, what you do is that you count the longest continuous carbon chain, and you name that as the parent structure. So in counting, we have 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6 carbons. Now after you have had a 6, it straight away tells you that the parent name is a hexane. Then you go on to number the carbon atoms in such a way that the substituents that are attached to the compound will be on the least carbon. So you try from the left side, you try from the right side. From the left side, you realize that if you number the first carbon, second carbon, third carbon, fourth carbon, it is on the fourth carbon from the left side that you have the 2 substituents on. So each of the meters are resting on the fourth carbon from the left. Now when you come and count it or number from the right, you have carbon number 1, carbon number 2, carbon number 3. You realize that the 2 meters are rather resting on carbon number 3 counting from your right side. And that is what is preferred. As much as possible, you always want the substituent to be on the least carbon. So that is what is preferred. Now because the meters are 2, if you are naming this, first of all you count the longest continuous carbon chain, hexane, 6 carbons, you put it aside. Then you come and number the carbon atoms. Now we have realized that these 2 meters are resting on carbon number 3 from the right side, and that is what is preferred. And so you name the substituent before the parent. And the substituent, as you see there, they are meters. So in naming, you specify the position of the meter as well. Now we numbered the carbons from the right side. So the meter 1 on top of the third carbon is on carbon number 3. The meter beneath that same carbon number 3 is also there. So realize that the 2 substituents are on the same carbon number 3. So if you are naming this, it is going to be a 3 for the first meter on top, another 3 for the second meter down the carbon, and that will make it a 3, 3. Now we have had 2 of the meters. So before I mention meter, because there are 2 there, I will introduce a die. So this will be a 3, 3 diameter. 3, 3 diameter. Then afterwards, I add the parent, which is a hexane, to it. So this is a 3, 3 diameter hexane. So in the example above, the 2 meter group is born on the third carbon, like I've already explained. Hence, the name will be a 3, 3 diameter hexane. 3, 3 diameter hexane. Let's look at another example. You also realize that in example 2, we still have 1, 2, 3, 4, 5, 6 carbons. So the longest continuous carbon chain is 6. Again, that tells you that the parent name is a hexane. Now these 2 meters, which are substituents, they are not on the same carbon, they are on separate carbons. So you are going to number the carbon atoms in such a way that you will get the meters, which are the substituents, to be on the least carbon. To be on the least carbon. So if I count from my left side of the compound, I'll have 1, 2, 3. The meter will be on the third carbon. 4, 5, and the second meter will be on the 5th carbon. So in identifying the position of the meters, I'll have 3 meter and then 5 meter. On the other hand, if I pick it from the right side, 1, 2, you realize that the first meter I'll meet is on the second carbon. 3, 4, then the second meter is on the 4th carbon. So in example 2, counting from the right side, we will have 2, 4, 2, 4. But if you pick it from the left side, we will have 3, 5, 3, 5. So realize that if you have 3, 5 and you add them, it gives you 8. If you have 2, 4 and then you add them, it gives you 7. So it means that the least carbon will be when you number the carbon atoms from the right side. That will give you a 2, 4 diameter hexane. 2, 4 diameter hexane. So in example B above, the 2 meter groups is born on the second and the 4th carbon. Hence, the name becomes 2, 4 diameter hexane. 2, 4 diameter hexane. Now, if the substituents are not the same, then they name them in alphabetical order. and then indicate the positions of each substituent. So where we have different substituents, you use alphabet. For example, in the ether, or this example that you see, we have organic substituent as ether, another organic substituent as meter. They are all substituents on this compound. And the longest continuous carbon chain is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Alright. So you realize that that is a hexane, you put it aside. Now we have two different substituents. One being ether and one being meter. Now anytime it is like that, you use alphabetical order. And alphabetically, ether, E comes before M. So it means that you must give preference to the ether in the naming of this particular compound. And so when, after getting the parent structure, that is the hexane, now you number the carbon atoms. If you pick it from the left side, it will be 1, 2, 3, 4. The ether that we are giving preference to will be on the 4th carbon. Then the meter will be on the 5th carbon. However, if you pick it from the number 8 from the right side, you realize that the ether we are giving preference to is on the 3rd carbon. So 1, 2, 3. Then the meter will be on the 2nd carbon. So 3 plus 2 gives you 5. And then 4 plus 5 gives you 9. So you realize that it is preferred to number from the right side, so that it will be 1, 2, 3. So we have 3 ether and then 2 meter. So in the example above, the substituents on the parent hexane are meter and ether. The meter is the CH3 and the ether is the CH3CH2, which is C2H5. Now in naming the compound above, the ether comes before the meter alphabetically. Therefore the name becomes 3 ether 2 meter hexane. 3 ether 2 meter hexane. Now there are situations that you have mixed substituents. That is to say that you have both the organic, which is an alkyl, and then the inorganic substituent. In a situation like that, we give preference first to the inorganic substituent, also in alphabetical order. So for example, if we have bromo, Br, we have chloro, we have meter. The very first one that we will consider, and for that matter, we will number of carbon atoms for it to be on the least carbon, is the bromo. Even though bromo, chloro are all inorganic, when it happens like that, you use alphabetical order and B comes before C. So we will have bromo, we have chloro before we go and consider the meter, which is organic substituent. So when we have a mixed substituents, or when you have organic and inorganic substituents at the same time, we first of all consider the inorganic substituent using alphabetical order before we come to the organic substituent. So in the example above, Br, which is bromo, is an inorganic compound, and CH3 an organic substituent. Hence, Br is named before the CH3. So take note that anytime organic and inorganic substituents appear on a particular compound, we give preference to the inorganic substituent before the organic substituent. While there are 2 or more of the inorganic, we use alphabetical order. 2 or more of the organic, again, we also use alphabetical order. So the name for this particular compound will be 2-bromo, because if you count from the left side, the bromo will be on the 2nd carbon. If you count from the right side, it will be on the 1, 2, 3, 4, 5, 5th carbon. So you know we always want the least, so you have to number it from the left side. And that will make it a 2-bromo and then 4 meter hexane. 2-bromo, 4 meter hexane. Now these are some questions that I am giving to you to try your hands on. You are to name the Aromatic names of the following. A, you see the compound there. B, the compound is there. And the C and D, and the structures that you see over there. These are for your consumption. So you take time and then try to give the Aromatic names of the compounds that you see on the screen. Now we are done with naming of saturated compounds, that is alkanes. We are moving on to naming of unsaturated aliphatic compounds, alkenes and then alkynes. The rules for naming unsaturated hydrocarbons are the same as that of saturated hydrocarbons. There are just very few exceptions. Now, one of the exceptions is that the parent structure is named by replacing the suffix ane of the corresponding alkane with ene for alkyne, and then ene for alkene, and then yne for alkyne. The longest continuous chain should always include the 2 carbon atoms containing the double bond or triple bond. Very, very important. So if you look at the example that you see there, in the example above, the parent structure contains 4 carbon atoms. Remember, we have said that the longest continuous chain should always include the 2 carbon atoms containing the double bond. So the double bond must be featured in the parent structure. For if you look at the example over there, we have 1, 2, 3, 4 carbons, and it is that one that has a double bond in it. So the parent is butene. Then aside that, you see that there is a substituent, and the substituent is on the second carbon, numbering from the right side of the compound. And this substituent is an alkyl. It is called ether, and this ether, numbering from the right side, is bound on the second carbon. So in numbering the carbon atoms in the parent structure, the number begins at the carbon atom in the double bond. That is to say that you start numbering from the end of the compound that has the double bond closer to it. Now the position of the multiple bond is also indicated when naming the parent structure. So if you are naming it, you indicate the position of the double bond in it. So the parent name would then be 1-butene or but1-ene. By this, we are indicating the position of the double bond, and it's in front of the first carbon counting from your right. Then we have the ether as a substituent, which is on the second carbon, still counting from your right, and that is what is preferred. If you count from your left, the ether will be on the third carbon, and then the double bond will be in front of the third carbon. That will not be correct. So always the least is what is preferred. So by that, the name of this compound will be 2-ether-1-butene or 2-ether-but1-ene. It means that the ether is found on the second carbon, that's why it is 2-ether. 1-butene or but1-ene means that the double bond is placed in front of the first carbon. Now let's look at another example. Now you realize that the longest chain for this is 1, 2, 3, 4, 5. 5 carbons, and that tells you that it is a pentene. Again, in numbering, the double bond is closer to the terminal, that is the end of the carbon on the right side. And so it means that it is preferred to number the carbon atoms from the right side. Now, in numbering the carbon atoms from the right side, you realize that the substituent ether will be on the second carbon, and the double bond will be in front of the first carbon. So in the example above, the parent is 1-pentene or pent1-ene, and the substituent is ether. Hence, the name of the compound will be 2-ether-1-pentene or 2-ether-pent1-ene. 2-ether-pent1-ene. So take note that in this particular example, we have a CH3 that is on a post carbon at the end. But in principle, when we have an organic substituent at the end of a particular carbon, it is not considered as a substituent. It is part of the parent. But if it is inorganic, like bromo, like iodo, like chloro, then that one can be at the end of the compound. So the name of this is 2-ether-1-pentene or 2-ether-pent1-ene. Another example, here it's taking us to alkynes because of the triple bond. So if you look at the example that is there, you realize that it has a triple bond alkyne that is found between carbon atoms in the compound. So we also have Br, which is a substituent on one of the carbons. So first of all, you locate the longest continuous carbon chain that bears the triple bond, and that would be 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So it tells you that the parent is a hexane. Now let's look at the position of the triple bond. The position of the triple bond, if you count from the left side, 1, 2, 3, it is in front of the third carbon. From the right side, 1, 2, 3 is in front of the third carbon. So then, with regards to just the triple bond, then you can just count from any of the ends. But you realize that there is a substituent. So after giving consideration or preference to the triple bond, you all move on to the next substituent that you have to give preference to, and that is the bromo. So you realize that if you count from your left side, you number the carbon atoms from your left side, the bromo will be on 1, 2, 3, 4, 5, the fifth carbon. However, if you number, and that will not change the position of the triple bond to be in front of the third carbon. However, if you number from the right side, you realize that still the triple bond will be in front of the third carbon, but then this time around the bromo will be on the second carbon. So that is what is preferred. So the name of this will be 2-bromo 3-hexane, 2-bromo 3-hexane, or 2-bromo hex 3-ine, 2-bromo hex 3-ine. Now we continue with the rules. The rules are the same for the alkanes and the alkynes, except the parent structure that is named by replacing E in the corresponding alkane for and all. Here we are looking at naming compounds with functional groups. So the next one we are on is for all is the alkanols. The alkanol ends with OL and the alkanoic acid ends with OIC. So the parent structure is named by replacing the E in the corresponding alkane with OL for alkanols. And then you replace the E with OIC for alkanoic acid. So you have alkanoic acid, then you have alkanols. Now, when you pick alkane, when you pick CH4, which is methane, and then OH is added to it, and then one hydrogen is taken off, it gives us a methanol. Now, we also have alkanoic acid, and the least that you can get is an HCOOH, which is a methanoic acid. The next one is ethanol for alkanols. The next one is ethanol, and that is from ethane. So here again you pick one hydrogen and then you add OH to it. Now for ethane, its corresponding alkanoic acid is ethanoic acid. For methane, the corresponding alkanol is methanol. The corresponding alkanoic acid is methanoic acid. But ethane, the corresponding alkanol is ethanol, and then corresponding alkanoic acid is ethanoic acid. Then we have one propanol as propane, and the corresponding alkanoic acid is propanoic acid. And you see their structures on the board. So again, I am pausing also for you to look at these questions that you are supposed to give a trial to them. So you give the Aliphatic names of the following. We have A, B, C, and then 2. Identify and draw the structure of the functional group in the following compound. And the compounds are there. Then you draw the structures of the following compounds as well. Hex 3-ine, 2-methyl prop 1-ine, and 3,3-dimethyl butan 2-ol. Now we move on to talk about isomerism. What is isomerism? Now it's the occurrence of 2 or more compounds with the same molecular formula but different structural formula. The occurrence of 2 or more compounds. You have 2 or more compounds, and they have the same molecular formula but their structural formula differs. Then the phenomenon is classified as isomerism. So for example, the molecular formula for C4H10 that is butane, can have two isomers. First, butane structure is an isomer of itself, and that is what you draw first. So we have CH3, CH2, CH2, CH3, and that's a butane. Now, if I'm drawing the next isomer of butane, I need to cut the CH3, one of the CH3s, and then come and take off one of the hydrogen atoms on the middle carbon and place the CH3 on it and take that hydrogen atom to where I took the CH3 from. And that is what you see there in that structure. And once that is done, it will form 2-meter propane. 2-meter propane, because the longest carbon chain is propane. And now a substituent meter, which is on the second carbon. So 2-meter propane. Now rather than structures A and B above are isomers that have the same molecular formula, C4H10, but different structural formula. So if you look at the isomers that you have formed, you cannot get a higher number than the carbon, neither the hydrogen. Neither will you also get a lower number. It is the same, and that's what we're referring to the same molecular formula. But when it comes to their structures, they are arranged differently, in that they have different structural formula. If you want to get more information on this isomerism, there's a link down there. You just click on it, and then it will take you to where you get a lot of information. Now we have two main types of isomers. In fact, isomerism is the phenomenon that occurs when two or more compounds exhibit the same molecular formula but different structural formula. But isomers are the compounds that exhibit isomerism. They are the compounds that exhibit isomerism. So we have two main types of isomerism, and they are structural isomerism and stereo isomerism. When we talk of structural isomerism, what are we referring to? It is defined as the occurrence of the compounds of the same molecular formula but different structural formula, and that's a structural isomerism. Occurrence of compounds of the same molecular formula but different structural formula is what is referred to as structural isomerism. There are three subdivisions of structural isomerism, and these are: one, chain isomers or chain isomerism. This arises because of the possibility of branching of the carbon chain. For example, the molecular formula for pentane is C5H12. The isomers example of that molecular formula, we can have pentane. I said that it is an isomer of itself. Then we can also obtain 2-meter butane. Then you can have 2,2-dimeter propane. You use the steps which I have just discussed with you in arriving at these isomers to do that. And once you do that, you get pentane, you get 2-meter butane, and then you obtain 2,2-dimeter propane. Then we have positional isomerism. Positional isomerism. And this arises because of the possibility of changing positions of the functional groups on carbon chain. Position of the functional groups on carbon chain. So for example, we have the molecular formula C3H8O. Now you realize that we can change the position of the OH, and once we change the position of the OH for the same compound to be possible, then we have positional isomerism. And these compounds that are exhibiting the positional isomerism are what we refer to as the positional isomers. So we can have one propanol, we can also have two propanol. Now we also have functional group isomers or functional group isomerism. This arises due to the possibility of interchanging certain pairs of functional groups. Possibility of interchanging certain pairs of functional group. So again, the example molecular formula C4H10O. The isomers are 1-butanol. Then we can also have diether or diethoxyethane, diether oxide. And these are examples of this functional group isomers. Then we also have stereoisomerism. This is the occurrence of two or more molecules of the same structural formula. The same structural formula but different arrangements of atoms in space. So here, the structural formula is the same, but when it comes to the arrangements of the atoms in space, they are different, and that is stereoisomerism. Then we have two main types of stereoisomerism. These are the geometric isomerism or geometric stereoisomerism. Now, this is the occurrence of compounds of the same structural formula but different arrangement of atoms in space due to the hindrance to rotation. So, for example, we have the cis and the trans, and they are geometrical isomerism that are normally exhibited in alkenes. So, take note of it. You realize that if you take a critical look at the compounds over there, we have one in which the CH3 are at the same side. Then we have one in which the CH3 are on opposite side of the compound. The one with the CH3 at the same side is 6-butene. So in this case it is 6,2-butene. Then we have trans-2-butene as well. Trans-2-butene. So trans isomers. Alkenes are saturated hydrocarbons. Now that we have done with this, we are again picking up the hydrocarbons classes and then discussing them in detail. So when you pick alkenes, there are some properties that we can talk about with alkenes. Now they are saturated hydrocarbons containing carbon-carbon single bonds. We have said it. In examination, you can be asked to explain saturated hydrocarbons or why alkenes are considered as saturated hydrocarbons. Then you say that they contain carbon-carbon single bonds. Now they form homologous series with general molecular formula CnH2n plus 2. A homologous series is a group of compounds that differ from each neighboring member by a unit of H2 or CH2. So all carbon atoms of alkanes undergo sp3 hybridization, and the shape of alkane molecule is tetrahedral. Now the carbon-carbon bonds are sp3 sigma bond that overlap. Sources of alkanes. Where do we obtain alkane from? What are the sources? Now methane is sourced from natural gas formed by biological decomposition of marine organisms and destructive distillation of wood, burning of wood and a limited supply of wood. And other alkanes are also produced from crude oil. A typical example is petroleum. Now, isomerism of alkanes. Alkanes exhibit chain isomerism. This is due to the possibility of branching from straight chain. Chain isomerism, the possibility of branching from straight chain. So example 1, we have butane, C4H10. Now, it has one isomer you see there and another isomer you see there. So in fact, they have two isomers. The very first one is the butane itself, which is CH3, CH2, another CH2, and a CH3. Then the next isomer that can be obtained from alkane is 2-methyl-propane. 2-methyl-propane, and the structure of 2-methyl-propane is what you see there. Apart from these two, you cannot have any other structure or isomer of an alkane. Now, physical properties of alkanes. Alkanes exist in all the three states of matter under normal conditions. So under normal conditions, we can have alkanes that are gases, alkanes that are liquids, and some that are quasi-solids. Now, from carbon number 1 to carbon number 4, they are all gases. So here we are talking about methane, ethane, propane, butane. They are all gases, carbon number 1 to carbon number 4. Now from pentane, that is carbon number 5 to carbon number 17, they are liquids, and 17 upwards are quasi-solids. Alkanes are less dense than water and also insoluble in water. It means that you pour them in water, you put them in water, and they will not dissolve. Now they have low melting point and boiling point, but increases as the molecular mass increases along the homologous series. These are physical properties of alkanes. Now if you want to look at chemical properties of alkanes, alkanes burn completely in excess oxygen to produce carbon dioxide, water, and energy. It burns excessively in oxygen to produce carbon dioxide, water, and energy. So you see the example CH3, which is ethane plus oxygen, molecular oxygen, will give you carbon dioxide, will give you water, and then to give you energy as well. So however, a limited supply of oxygen, alkanes undergo incomplete combustion, producing poisonous carbon 2 oxide, and this is called addition reaction. So we can say that alkanes undergo addition reaction. However, in a limited supply of oxygen, alkanes undergo incomplete combustion, now producing poisonous carbon 2 oxide. This is also called addition reaction, and typically that is the example that you see on the screen. Now this occurs in everyday devices like cars, like kerosene, like lamps, gas cookers, starting a car in the enclosed garage, and then using cooker and kerosene stove in a poorly ventilated kitchen. Alkanes undergo substitution reactions. They undergo substitution reactions. So the very first one is halogenation reaction. Halogenation reaction. This is done under ultraviolet radiation as well. So if you have methane CH4 plus chlorine molecule, that is Cl2, you realize that one of the chlorine molecule will dissociate and then add to the methane, that is a CH4. Then one of the chlorine molecule will also attach itself to the other compound. So we will have CH3Cl plus HCl. So one hydrogen from the CH4 joins the one of the chlorine atom to form HCl, and then the other chlorine atom also joins the CH3 to form chloromethane. And the structures are what you see there. So alkanes undergo cracking. Cracking is a reaction in which a large molecule of alkane is broken into smaller molecules. An example is what you see in the reaction. Now, uses of alkanes. Alkanes, 1, are used as fuels for automobiles. 2, as a source of heat for cooking. 3, as a starting material for many organic synthesis. So these are some of the uses of alkanes. Now, laboratory preparation of alkanes. Now, we can prepare alkanes in the science lab using the hydrogenation of alkanes. And here we have an alkane that is C2H4 plus a hydrogen to it. And then this one will give us CH3, which is ethane. Then the next one is decarboxylation. And decarboxylation, we have CH3CH2CONA plus sodium hydroxide. And that will give us CH3CH3 plus Na2CO3. And so on and so forth with the various formula. Next one is alkenes. Alkenes are unsaturated hydrocarbons containing carbon-carbon double bond. We have said this. Now they form a homologous series with general molecular formula CnH2n. CnH2n, where n is greater or equal to 2. They exhibit sp2 hybridization. And alkenes, the shape of alkene molecule is trigonal planar. Trigonal planar for alkene molecule. They are more reactive due to the presence of delocalized electrons in the pi bond. Alkenes are more reactive than alkanes, and it is due to the presence of delocalized electrons in the pi bond. The double bond consists of one strong sigma bond and then one weak pi bond. The bond is also shorter and stronger than the single bond. So let's look at the alkenes using the formula CnH2 and where n starts from 2. So when n starts from 2, the molecular formula of the least alkene you can get is ethene. Ethene. Now when n is 3, you have C3H6. And so you have propene. And when n is 4, C4H8, you have butene. And n is 5, C5H10, you also have pentene. So you will take time and draw the structural formulae of this. Now, as a way of intro into the structural formulae, we have alkene C2H4. So realize that there are 2 carbon atoms or double bonds that is sandwiching between the two carbon atoms. That is sandwiched between the two carbon atoms. Then when N is 3, we have propene, and that is the structure that you see there. We have 3 carbon atoms. Then we have a double bond in between the first carbon and the second carbon. Then we have when N is 4, that is butane, and that is the structure you see there. When N is 5, pentene or pent1-ene, and that is also the structure that you see there. So in dealing with alkenes, most of the time you always have to ensure that you have double bond in it. Now, where do we obtain alkenes from? ENE. Alkenes are produced by cracking of large alkenes. So if you have alkenes and then you crack them, they end up giving you alkenes. So you do the cracking under high temperature. So if you have C12H26, you crack them to obtain C10H22 plus an alkene, that is CH2 double bond CH2. Now, conversion of alkanols, dehydration of alkanols. So we have ethanol, then we have ethene plus H2. Conversion of alkyl halides to alkenes will also give us CH3 CH2 CH2Br, 2 CH3 CH2 double bond CH2. Now, physical properties of alkenes. All alkenes have lower boiling and melting point. It means that when you are burning them, it doesn't require much heat or temperature to be able to melt or boil them. These increase steadily with increasing chain length. Now, due to increasing strength of van der Waals forces. They are polar. Alkenes are polar, therefore insoluble in water. They dissolve in non-polar solvents like benzene and tetrachloromethane. Now, the lower members up to butane are gases. For alkene, the lower members up to butane are gases. Now, C5 up to C15 molecules are volatile liquids. Above C15 molecules are solids. We are still on the chemical properties of alkenes. Alkenes are chemically more reactive than alkanes. This is because alkenes are unsaturated hydrocarbons that have a double bond between the carbon atoms or between two carbon atoms. Almost all of the chemical reaction of alkene occur at the double bond. Alkenes can undergo combustion, addition, and polymerization. Combustion of alkenes. The word combustion is about burning. So like any other hydrocarbons, alkenes burn in air or oxygen. Like alkanes, an alkene burns completely in the sufficient oxygen to produce carbon dioxide and water. Alkene also burns incompletely in limited supply of oxygen to produce carbon monoxide. That is the form of a soot and then water. Example, complete combustion of ethene will give me carbon dioxide and water. Complete combustion of ethene will give me 2 molecules of carbon dioxide and 2 molecules of carbon monoxide and water. Addition reaction of alkenes. Alkenes undergo addition reaction. It was alkenes that undergo substitution reaction. So alkenes are unsaturated hydrocarbons, hence they undergo addition reactions. Addition reaction occurs when other atoms are added to each carbon atom of the double bond. So we have CC double bond to form single covalent bond. A typical example is the structures that you see, A and then B. So alkenes undergo addition reaction with halogens, with steam, with halogen halide and potassium permanganate 7. Potassium permanganate 7. Uses of alkenes. What do we use alkenes for? One, alkenes are used as a starting material in the synthesis of plastics, likewise, and alcohols. They are also used as fuels. Now, ethene, the most important organic feedstock in industry for many chemical products such as polyethylene, vinyl chloride, and then styrene ethanol. Alkynes are also unsaturated hydrocarbons containing carbon-carbon triple bond. They also form a homologous series with general molecular formula CnH2n-2, where n is greater than or equal to 2. Then the shape of the alkyne molecule is linear. The shape of alkyne molecule is linear. The triple bond consists of one strong stigma bond and then two weak pi bonds. The functional group in alkyne is carbon-carbon triple bond, and it is represented as CC triple bond. Now, alkynes, number of carbon atoms, the molecular formula, and then the name. So when N is 2, we have C2H2, and the name is ethyne. When N is 3, we have C3H4. We are talking about alkynes, and the name is butane. And when N is 5, we have C5H10, and the name is pentyne. So the structural formulae of all of them are what you see there. You can look at it again. Isomerism in alkynes. Alkynes show position and chain isomerism, but not geometric because it's linear. The molecular formula is C4H6. If you look at examples that we have there, we have 2-butane. 2-butane. The carbon atoms are 4. That makes it a but. And then the ending is YNE because it has a triple bond. Next one is 1-butane. So 1, 2, 3, 4. 1, 2, 3, 4. So that is the isomers of alkynes. Sources of alkynes. Alkynes are produced on a large scale by cracking alkane from petroleum fractions. Example, 2CH, 1800 Kelvin, and then a triple bond sandwiching between two carbons, that is ethyne, and then 3 hydrogen molecules. Now, ethyne is produced from the reaction of water on calcium carbide. So calcium carbide is what you see there. Water is added, cold water, and then it gives you calcium hydroxide and then ethyne. Now, refluxing 1,2-dibromoalkane with alcoholic KOH. For example, we have CH2Br, and then we have ethyne plus 2HBr. Now, physical properties of alkynes. The alkynes containing up to 4 carbon atoms are gases, while those with more carbon atoms, depending on the size of the molecules, are either liquids or solids. The alkyne homologous series show gradual increase with molar masses. So as they move down the series, there's an increase in their molar mass. Now, symmetrical alkynes have slightly higher physical constants, boiling and then melting points and density. Symmetrical alkynes, they have slightly higher physical constants, boiling and melting points and densities. Alkynes are mainly insoluble in water, but are freely soluble in organic solvents. Alkyne molecules containing 4 or more carbon atoms show chain isomerism. In this way, we have butane, C4H6. It has 2 isomers. And the isomers are what you see there. Now, alkynes are more reactive than alkenes since they are more unsaturated than the alkanes. They undergo a double addition reaction to give saturated compounds. For example, we have ethyne plus 2 hydrogens. And the 2 hydrogens, when they attack the compound, they break the bond. So you arrive at CH2, double bond CH2. Then again, the H2 will attack the double bond to break it. Eventually, you arrive at CH3, which is ethane. Test for unsaturated compounds. Unsaturated compounds rapidly decolorize a reddish brown bromine liquid in carbon CC4. Unsaturated compounds also decolorize an acidified purple solution of potassium tetraoxomanganate 7 to green, which later turns brown PPT. So you can also get more information on these things that we are taking you through by clicking on the link. that you see there. Now we're looking at uses of alkynes. So we have ethyne, which is an alkyne, and it is used as oxyacetylene flame for cutting and welding of metal. So you realize that the flame that the welders use for welding metals, that flame, we use ethyne in making it. Now it is also used as a raw material for synthesis of rubbers. So PVC, plastics, rubbers, we use some alkyne in making them. Alkynes are also used as a source of fuel for hunters' lamp. The lamp that the hunters use for hunting, they put some amount of alkynes in it to enable it to light properly. Finally, it's also used in the production of trichloroethane. I believe that this will end the first phase of this organic chemistry discussion. We will continue the second phase in our subsequent bulletin that we will have. I think that we will have to end here, and then later we will continue the second phase. And that second phase will be on alkanols, everything about alkanols. We talk about the nomenclature, the sources, the types, and then the reactions, the properties, both physical and chemical as well. Then after that, we also look at alkanoic acid, which we will also look at their nomenclature, their reactions, their types, as well as their sources. So that is what we'll be looking at in our next discussion. Thank you very much for your attention. Bye-bye.